this video, we'll study the mechanics of train movement. So let us consider the driving mechanism of an electric vehicle, which is as shown in the figure. Here, the armature of the driving motor has a pinion meshed with the gear wheel on the driving wheel. So the diameter of the pinion is D1 and of the gear wheel is D and of the road wheel is capital D. Let T be the torque exerted by the driving motor which is transferred to the road wheel through the gear, and F1 be the tractive effort at the pinion. So we have T equal to F1 D1 by 2, and the tractive effort on the driving wheel is given by F equal to neta F1 D by D, which is equal to 2 neta T by D1 into D by D, that is equal to 2 neta T by D into D by D1. Let gamma be equal to D by D1, which is the gear ratio. Therefore, we have F equal to 2 neta gamma T by D, where neta is the efficiency of transmission. Next topic is tractive effort. For the propulsion of train. So the tractive effort for the propulsion of train, we have in that tractive effort for acceleration, tractive effort to overcome the gradient, and tractive effort to overcome the train resistance. So first we have tractive effort for acceleration. So consider a train of weight W tons, which is to be accelerated at alpha kilometer per hour per second. Then the weight of the train is equal to 1000 W kg, and the acceleration in meter per second square is alpha into 1000 by 3600, that is equal to 0.2778 alpha meter per second square. Therefore, the force or tractive effort required for linear acceleration is given by F equal to mass into acceleration, that is equal to 1000 W into 0.2778 alpha. So we get the tractive effort for linear acceleration as 277.8 W alpha newtons. So when the train is accelerated, The rotating parts will also be accelerated but in an angular direction. Therefore, there is need of additional tractive effort apart from the tractive effort required to produce linear acceleration. For angular acceleration, the moment of inertia of the rotating parts will be considered, which will increase the accelerating weight of the train. So the accelerating weight of the train is normally higher than the dead weight, around 8 to 15%. So we have the normal value of accelerating weight WE is equal to around 10 to 12% of the dead weight of the train. That is, WE is 10 to 12% of W. Therefore, the tractive effort for acceleration is given by 277.8 WE alpha newtons. The dead weight is replaced by the accelerating weight WE, which is around 1.1 to 1.2 W. Next is tractive effort to overcome the gradient. So when the train is moving up a gradient, so as shown in the figure, when the train is moving up a gradient, the tractive effort required to overcome the gradient has to negotiate the weight of the train acting along the track. So we have the tractive effort Fg equal to 1000 W sin theta. So in railway traction, the gradient of the track, it is defined as the rise of the track in meters for a track distance of 100 meters, and it is denoted by percentage gradient G. So we have gradient, that is sin theta equal to elevation by distance along the track. So percentage gradient or percentage G is equal to 100 sin theta. We have Fg equal to 1000 W sin theta, that is 10 W into 100 sin theta, that is equal to 10 Wg kgf. So Fg is equal to 10 into 9.81 Wg in newtons. Therefore, we get the tractive effort to overcome the gradients Fg equal to 98.1 Wg newtons. So the value of Fg is positive for train moving up the gradient and it is negative when train is moving down the gradient. Next is tractive effort. To overcome train resistance. So the train when accelerated and running at a uniform speed on a level track, it requires tractive effort to overcome the resistance due to friction at the various parts of the rolling stock and friction due to the track and also due to air resistance. So the resistance to the train movement, it depends upon the shape, size of the rolling stock, condition of the track, direction and velocity of the wind. Normally the value of this train resistance is between 40 to 70 Newton per ton. So the tractive effort required to overcome the train resistance is Fr equal to Wr, where R is the specific train resistance in Newton per ton. Therefore, the tractive effort required for the propulsion of the train F is equal to Fa plus or minus Fg plus Fr, that is equal to 277.8 We alpha plus or minus 98.1 Wg plus Wr. So this is the total tractive effort required for the propulsion of the train. Next topic is power output at the driving axles. So power is defined as the rate of doing work. So power is equal to work by time, and work is nothing but force into distance. So we get power is equal to force into distance by time, or power is equal to force into speed, because distance by time is speed. Therefore, at any time instant, the power output from the driving axles is given by tractive effort into speed. That is Ft into speed in meter per second. So if the speed is v kilometer per hour, then the power output is given by Ft v into 1000 by 3600 watts. Next topic is energy output from the driving axles. When the train run is according to the trapezoidal speed time curve, we have the energy output from the driving axles during acceleration period given by E1 equal to average power into time. So we have E1 is equal to half Ft Vm by 3600 into T1 kilowatt second, where Vm is the speed in kilometer per hour at the end of acceleration period. Similarly, for the free running period, we have energy output. So energy output during free running period is E2 equal to power into time, that is E2 equal to Ft dash Vm by 3600 into T2 kilowatt second, where Ft dash is the tractive effort exerted during the free running period. Therefore, the total energy output from the driving axles is E equal to E1 plus E2, since there is no energy output during the braking period. So E is equal to half Ft Vm by 3600 into T1 plus Ft dash Vm by 3600 into T2. This is in kilowatt second. The energy output, it can be expressed in watt hours. So we have E is equal to half Ft Vm into 1000 by 3600 into T1 by 3600 plus Ft dash Vm into 1000 by 3600 into T2 by 3600 in watt hours. Next topic is determination of specific energy output on a level track using a simplified speed time curve. So specific energy output is defined as the energy consumed by the train in watt hours to haul 1 ton of the train through 1 kilometer. So specific energy output is equal to energy output in watt hours, which is nothing but the energy consumed by the train divided by dead weight of the train in tons into distance travelled in kilometer. So the unit is watt hour per ton kilometer. Consider the trapezoidal speed time curve for the train run. So the train run is made on a level track according to the trapezoidal speed time curve. So we have the energy output required to accelerate the train from rest to a speed of Vm which is given by E1, that is equal to average power into time. So E1 is equal to half Ft Vm by 3600 into T1 by 3600 kilowatt hour. That is E1 is equal to half Ft Vm by 3600 into 1 by 3600 into Vm by alpha. So that is equal to half into Vm square by 3600 square alpha into Ft, where Ft is equal to 277.8 We alpha plus Wr. Therefore, E1 is equal to half into Vm square by 3600 square alpha into 277.8 We alpha plus Wr in kilowatt hours. Similarly, output energy required during free run is E2 equal to power into time, that is Ft dash Vm by 3600 into T2 by 3600 kilowatt hour, that is E2 is equal to Ft dash by 3600 into D dash, where D dash is equal to Vm T2 by 3600, which is the distance travelled during free run. So we have E2 is equal to Wr by 3600 into D dash. Since at the start of free run, the train has reached its maximum speed, therefore the term tractive effort required for acceleration is not included in Ft dash. So now the total output energy required for the run is given by E equal to E1 plus E2. That is E is equal to half into Vm square by 3600 square alpha into 277.8 We alpha plus Wr plus Wr d dash by 3600 in kilowatt hour. So that is equal to Vm square into 1000 by 2 alpha into 3600 square into 277.8 We alpha plus Wr plus Wr into 1000 by 3600 into d dash in watt hours. So E is equal to Vm square by 2 alpha into 1000 by 3600 square into 277.8 We alpha plus Vm square by 2 alpha into 1000 by 3600 square Wr plus 1000 by 3600 Wr d dash. So we have E is equal to 0.01072 WeVm square plus Vm square by 2 alpha into 1000 by 3600 square Wr plus 1000 by 3600 Wr d dash. So we have E is equal to 0.01072 WeVm square plus 1000 by 3600 Wr into Vm square by 2 alpha into 1 by 3600 plus d dash. We have d double dash, that is the distance travelled during acceleration, equal to half Vm T1 by 3600, that is half Vm by 3600 into Vm by alpha, that is Vm square by 2 alpha into 3600. Therefore, we have E is equal to 0.01072 WeVm square plus 1000 by 3600 into Wr into d double dash plus d dash. So therefore, E is equal to 0.01072 WeVm square plus 0.2778 Wr d1, where d1 is equal to d double dash plus d dash, It is the distance traveled during acceleration and free run period. Therefore, specific energy output is equal to the energy output in watt hours by the weight of the train in tons into distance traveled in kilometers. Therefore, we get the equation for specific energy output as 0.01072 WeVm square plus 0.2778 WRD1 whole divided by WD. It is in watt hour per ton kilometer. So the specific energy output, it can be written as 0.01072 Vm square by D into We by W plus 0.2778 R into D1 by D in watt hours per ton kilometer. We have one more term, that is specific energy consumption. So it is given or defined as specific energy output at the driving wheels by the overall efficiency of the traction motors and gearing. So we have specific energy consumption as 0.01072 Vm square by D into We by W plus 0.2778 R D1 by D whole divided by neta G into neta M, where neta G is the efficiency of gearing system and neta M is the efficiency of traction motors. Next topic is factors affecting specific energy consumption. So we have the equation for specific energy consumption, which is 0.01072 Vm square by D into We by W plus 0.2778 R D1 by D divided by neta G neta M. So the factors affecting the specific energy consumption are: first is the distance covered D. So if the distance between stops is greater, then the specific consumption value will be lesser. Second factor is the train resistance. So the specific energy consumption, it depends upon the train resistance R, which in turn depends upon the nature of the track, speed of the train and shape of the rolling stock. Next factor is acceleration and retardation. So for the distance d1, the power remains on, which increases with the higher value of acceleration and retardation, which in turn increases the specific energy consumption. Next factor is gradient. Though for the equation of specific energy output, a level track was considered, that is G equal to 0, but while going up the steep gradient, more energy is needed for the movement of the train. Hence, the specific energy consumption increases. Next factor is the train equipment. More efficient train equipment will reduce the specific energy consumption.